Welcome back. I hope you had a chance to think about some of the properties of hydrochloric acid as a salt former while you were making that cup of tea. So, did you think of any? Let me tell you what I think. I think, number one, hydrochloric acid is used as a salt former because it's a strong acid and therefore it has a low pKa. And as we looked at already, if you've got a low pKa from your acid, you're almost certainly guaranteed to have a delta pKa of at least 3. So it should form a salt with a high fraction of salt formation, probably more than 99%. So that's the number one reason. And another one, which you might not have thought of, I think you probably would have got the first one, but maybe not the second, is that HCl contains physiologically ubiquitous ions. Now that is quite a mouthful, difficult to say. What does it actually mean? It means that although hydrochloric acid itself is very aggressive as an acid, when it disperses in water you form a proton and a chloride ion, and those two ions are everywhere in your body. So what it means is if you use hydrochloride as your salt former, you're not introducing to the body anything that it doesn't already have. Okay, lots of protons, lots of chloride ions already. So in that instance it should be relatively safe because the body should be used to dealing with it. So those are two good reasons, I think, why hydrochloride salts are the most common types of salts for basic drugs. What about some of the problems? The fact that I said, can you think of 4 problems, kind of implies there are some problems with hydrochloric acid salts. So a couple of these we've mentioned already, and a couple of them you might not have thought of. So the first one is that because it's such a strong acid, the drop in pH that it can cause when it dissolves can be quite significant, and that can cause some local irritation. I said that already, didn't I? So intramuscular injection, for instance, you can cause a quite significant drop in local pH, a lot like when you get stung by a bee, for instance. Imagine how painful that is. So the same thing would be true if that drop in pH was caused in your muscle tissue. So that's not very good. I've just given you a little example at the bottom of that slide with alpranolol, which is that the hydrochloride version is extremely irritant to the esophagus, while the benzoate salt is not, simply because it doesn't cause such a large reduction in pH. The other one that you might have got, which I mentioned earlier as well, is that it can be very corrosive during manufacturing, especially if you're manufacturing in a stainless steel vessel in some way, because hydrochloric acid reacts very strongly with stainless steel, so you can corrode it, for instance, and that's not very good. When you go through your wash down procedures at the end, you'll find the surface has been pitted, and in the limit you may actually eat away, say, some of the stainless steel pipes, and that would not be good either. The third one is a typical problem with salts in general, which is that it's very highly hygroscopic. So if your free base is susceptible to hydrolysis, then it's going to suck in quite a lot of water if it's made as a hydrochloride salt. And the last one, which you may not have heard of unless you really delved into this in the past, is a thing called the common ion effect. So I said just now that one of the benefits of hydrochloric acid as a salt former is that it contains physiologically ubiquitous ions, a proton and a chloride. But that's actually one of its biggest downfalls as well, because of the common ion effect. And effectively what that says is, if you're trying to dissolve something which is going to produce protons and chloride ions in a solution that already contains protons and chloride ions, it kind of is difficult to dissolve because the build-up of concentration of those ions already there hinders further dissolution. So let's take a further look at that. So the first thing to think about is how much chloride is actually present in bodily fluids. So I've given some examples on the slide. You've got roughly 0.1 molar chloride ions in gastric fluid. That should come as no surprise because gastric fluid is a solution of hydrochloric acid, right? So there's going to be quite a lot of chloride ions there. And that actually increases when you go into the intestinal fluid. It gets up to about 0.13 molar. Obviously that's going to vary person to person. But the principle here is that you have quite an appreciable number of chloride ions floating around along the GI tract. And that can be a problem. You might remember from basic chemistry classes that there is a principle called Le Chatelier's principle. And what that says is when a system is at equilibrium, if you try and change the position of equilibrium, the system will respond in such a way that equilibrium is maintained. So in this instance, gastric fluid or small intestinal fluid contain appreciable amounts of chloride ions, but they are at a position of equilibrium. If you then swallow a basic salt which is containing hydrochloric acid, if it dissolves, it's going to add more chloride ions to the solution. And the Chatelier's principle says the system will respond in such a way as to oppose that change. It won't allow the concentration of chloride ions to increase. And the easiest way it does that is by not allowing the salt to dissolve in the first place. So if you're trying to dissolve something which is going to release chloride ions into a solvent which is already containing chloride ions, it will slow the process of dissolution down. Okay, so that's the common ion effect. And so it's good in the sense that it's a common ion, so it won't do you much harm, but it's bad in the sense that it stops dissolution occurring. That's really one of the reasons why you're making the salt in the first place. You might say to me, okay, what I'll do then is I won't make a hydrochloride salt, I'll make a different type of salt. So I've given you an example here of haloperidol. You can go and look at this paper. I've given you the reference. It's quite an interesting paper. So you can make, say, a phosphate salt or a mesylate salt instead of a hydrochloride salt. Okay, and you think, okay, there should be no common ions. No phosphate or mesylate group is going to release chloride, so we should not have a problem trying to dissolve those salts in a high chloride medium. But when you do the experiments for real, you discover that there is actually a problem. Those two salts don't dissolve very well. So the question is, what's going on that means that those salts won't dissolve in gastric media when they don't share a common ion? And the answer is, it's all about the reactivity potential of the salts in the first place. So remember that the salt itself is just two ions that have come together to create an electrically neutral compound. If you take, say in this case, a phosphate or a mesylate salt, and you dissolve those in water, not plain water, but in bodily fluid, so gastric fluid, they contain a lot of chloride already. So what will happen is, even though you've dissolved a phosphate salt, for instance, the first thing that it will do is the phosphate will dissociate but be replaced with a chloride because it's more reactive. And then, because it's a chloride and it won't dissolve, it will precipitate out. So the patient swallows a phosphate salt, but then almost immediately a chloride salt precipitates. Okay, and so even though you think you've given the patient a phosphate salt, almost immediately it's dissolved in their body, it's precipitated back out as a chloride salt. And it's no different from having swallowed a chloride salt in the first place. So it's kind of important to recognise that because salts themselves are very reactive and there's a lot of chemistry that's going on in biological media, what you've given to a patient isn't necessarily what's inside them. It's what went into their mouth, but it's not necessarily what's inside their GI tract. This concept becomes really important in just a second when we look at the solubility profiles of acid and basic salts. Right, so you look at that paper and you see what you think. So let's talk about salt solubility and salt solubility profiles. If I said to you just a simple acid or base, what does its solubility profile look like? I'm kind of hoping you'll say to me, and let's choose a base first. So a base at low pH, the solubility is probably the highest. And as you increase the pH, the solubility starts to drop. So you're going to get some sort of curve like this, highly soluble at low pH, and then insoluble at higher pHs. And for an acid, it's the other way round. It's generally insoluble at low pHs, and it becomes more soluble at high pHs. Why is the question? And the answer is, it's the common ion effect. So the easiest way of thinking about this is with acids this time. So previously, the easiest way I felt of thinking about conjugate acids and bases was to think about bases. In this case, I think it's easier to think about acids. So you have an acid, AH, it's a proton donor, and you have it in a low pH solution. Low pH means a lot of protons floating around in solution. It's the Chatelier's principle, isn't it? AH can't dissociate, because if it dissociates, it creates a proton, and there's already a lot of protons in solution, so it stops it dissolve things, the common ion effect at work again. And the same is true for bases. It's just the other way around. It's just that sometimes it's difficult to remember that there might be a conjugate base in your molecule, but the principle is the same. So for an acid, low solubility at low pH, and then increasing solubility as pH increases, and for a base, vice versa. What happens for a salt? Because a salt is not quite as simple as a free acid or base. The answer is that it's complicated. So rather than try and explain it to you without a graph, I'm going to show you what it looks like, and then we can talk our way through it. So on the screen in front of you is an example of what the solubility profile looks like for a basic salt. As ever, I'm going to start with the basic salts, and then we'll look at acidic salts. Acidic salts are the same, they're just the other way around. Okay. So I'm going to explain this. If you don't follow it first time, that's totally fine. Most people don't, so that's absolutely understandable. Keep the video going, because we're going to talk about it again for acidic salts, but the situation is reversed. Or stop the video after the basic salts and watch it again, just so you've got it in your head, kind of what's going on here. Same principle as before. If you really can't grasp it, fire me an email and I'll do my best to try and explain it to you in a different way. So the way it works is the graph shows you solubility on the y-axis and pH on the x-axis. I would just want to point out before we go any further, solubility is a position of equilibrium. When we measure solubility, it's the concentration in solution with excess solid left over. The fact that there's excess solid left over is kind of important when we look at the explanation for this graph in just a second. So just remember, solubility is defined as the maximum concentration of a solute in solution in equilibrium with excess solid. So let's start on the left-hand side of this graph, where the pH is the lowest. So if we look at pH 1.5, we can see that the basic salt has a solubility of around about 5 milligrams per milliliter. As we increase the pH, the solubility remains relatively constant until we get to a critical point when we can see an intersection between two curves. Now you might say to me, this is a very complicated looking curve. Why is it created like this? And one of the reasons is because it's calculated from the Henderson-Hasselbalch equation, like all of my other curves that I showed you earlier. So the general interpretation of how a salt behaves as a function of pH is to say it's effectively how the free base is behaving superimposed on how the salt is behaving. So for a basic salt, it contains a conjugate acid. And so what it means is the solubility profile of that material is going to look like an acid because it contains an acid. That would mean the lowest solubility at low pH and then increasing. So if we create the curve for just the salt, we're going to have a curve that looks like this. On the other hand, if we create the curve for the free base, then it's going to behave just like a base, which is low solubility at high pH and high solubility at low pH. And so it's going to look like this. So we have two curves, one for the salt, one for the free base. And if we put them together, we end up with a situation like this, which is what's shown on the screen. It's the calculated line for the salt and the calculated line for the free base. The reason I've left the extra bits over, these bits here, is simply to show you that this is a calculated line from the Henderson-Hasselbalch equation. But in reality, what will happen is the material will follow the profile for the salt on the left-hand side and for the base on the right-hand side. And so we end up with this kind of profile like this. If you don't believe me, and it's difficult to imagine what this looks like in reality, and this is an ideal graph, so in reality it can be a little bit wobblier than this. Look at some of Sirajudin's papers that I mentioned earlier, because he has these types of graphs for real materials, and you'll see that they follow this type of profile. Okay, so although you may not quite accept where it comes from right now, you just have to trust me that this is what salts actually look like when we study them for real. So the point where these two curves intersect, the solubility profile of the salt and the solubility profile of the base, that point of intersection is really key, and it's given a special name. It's pH max. I said right at the start, understanding what pH max is, being able to define it, and what it means is a key outcome from this lecture. So the definition is relatively easy. It's the point of intersection between the solubility profile for the salt and the free base in this case. Also for the free acid when we look at acids, but right now we're looking at bases. So it's the point of intersection between these two solubility curves as shown by the arrow on the graph. You will see, if you follow that arrow down, that it corresponds to one particular pH value. It doesn't matter what it is, and it will vary from salt to salt, but it is the point of intersection between those two curves. Why is it important? And this is where it is a little bit tricky to follow, so bear with me. Watch this part of the video again if you need to. Imagine how we would make this graph if we were trying to measure it in a laboratory. The y-axis is solubility, the x-axis is pH. So we can control the pH while we measure the solubility. Solubility is the equilibrium between dissolved solute and excess solid. So if we were going to make this in the laboratory, let's say we start at pH 1.5, what we have to do is take the salt, we add it to some water, we stir it, and we keep adding salt until we have excess left over. We measure the concentration in the solution with the excess solid left over at the bottom. And we would in this case measure a value of around about 5 milligrams per milliliter. So imagine that's how we make the measurement at pH 1.5. Let's imagine we want to increase the pH to pH 2. We don't have to start the whole experiment again. We can just take that solution with excess solid at the bottom and we can add some base. By adding some base, the pH will rise. So all we need to do is add some base, increase the pH so that it becomes the next value that we want to measure. So for argument's sake, let's say pH 2. Let the system sit for a bit so we're happy it's at equilibrium. Measure the concentration in the solution, it's still 5. Then we add some more base. Let's say we increase the pH to 3, let the system sit, measure the concentration, still around about 5. It's fine. We can just carry on in that way, titrating in base, increasing the pH and measuring the corresponding solubility. That's fine at low pH. So for all these pHs roughly equal to or below 4, you just add some base, increase pH, measure the solubility, you'll find it's not really changing. Importantly, because the solubility measurement is always made with excess solid present, if you were to take some of that excess solid out and you were to look at it, or at least analyse it in some way, and ask yourself the question, what is this excess solid? You will find it's the salt. So for a basic salt, below the pH max, the excess solid is always the salt. Okay? This is a really key thing, and you might see what's coming now. But as we start to add base and we increase the pH so that we go across pH max. So imagine we've gone from pH 4 to pH 5 in this graph, and we were now to measure the solubility at pH 5, we would have found it's dropped enormously. It's well under 1 milligram per milliliter. The other thing that will happen is, if we take that excess solid out of that solution at pH 5 and we analyse it and we try and work out what it is, we will discover it's now the free base. This is a really fundamental point. The excess solid changes from the salt to the free base depending on which side of the pH max we are. For a basic salt, if we are below the pH max, any excess solid is salt. But above the pH max, any excess solid is a free base. It's kind of difficult to understand how that happens. So imagine that you're making this measurement in the way that I'm saying. You've got a beaker with the excess salt in it at low pH and you're titrating in the base and the pH is rising. It's kind of difficult to understand at what point does that solid go from salt to free base. Does it just happen like that? Is there a process that it goes through? It can't just happen instantaneously. Something has to happen. And you'd be right, something does happen. And the something that happens is that at the pH max, every molecule of base that you add, rather than increasing the pH, that molecule of base converts one molecule of salt back to the free base. So if you were to measure the pH, you were doing this like a titration, you had a burette and you were actually adding some base, what you'd find is that low pHs, below the pH max, you start to add the base and the pH is rising. Every time you add base, the pH rises until you get to the pH max. Then what you'll find is you start to add base, but the pH doesn't rise. You start adding, stirring, nothing happens. The reason is because those molecules of base that you're adding are not available to increase the pH. They're reacting with the excess solid and they're converting it from the salt to the free base. Once all of the excess solid has converted back to the free base and you carry on adding base, the pH will start to rise again. I hope you can imagine that if you had a lot of excess solid in your beaker, then as you're adding the base, the time it remains at a constant pH will be quite long because you've got to add enough base to convert all of the excess solid. If you have a very small amount of excess solid, it won't remain at 1 pH for very long. It will very rapidly start to increase. But it's kind of important to get in your head that it's the addition of base which is converting the salt back to the free base in this case. Okay, so if we were to actually make this measurement and we were to look at what the excess solid is, we will see that below pH max the excess solid is a salt and above pH max the excess solid is a base. In vivo, this is really important, and we're going to come back to it in just a second for what this means if you swallow a basic salt and it goes down your GI tract. But for now, just have a think. The GI tract starts acidic and it progresses to not alkaline but certainly more neutral pH as you go along the GI tract. Just have a think to yourself, what do you think that will mean for a solid salt, basic salt, if you were to swallow it? So just have a little think while I have a drink. Have you thought about it? You don't have to give me the answer right now. And the reason is because I want to review what I just said with acidic salts, and then we'll look at what it means for going down the GI tract. So, again, on the graph in front of you, it's the same graph, solubility profile, but now it's for an acidic salt. The basic layout of this graph is the same. It's just that on one side we have excess solid, which is a salt, and on the other it's now a free acid. The graph itself is the solubility profile of the two materials. One is the salt and one is the free acid. Think about the free acid first. I said already, at low pHs, the solubility of a free acid will be at its lowest because of the common ion effect, and it will start to increase as the pH rises. So the free acid is going to have a solubility profile like this, and the reverse is true for the salt because the salt, an acidic salt, contains a conjugate base, and so it's going to have a solubility profile like a base. So that would be lowest solubility at high pH and then increasing as it comes down. So one profile like this, one profile like this, put them on top of each other and we get this, which is what's shown on the screen in front of you. Same deal. Now you've got to do the same thing. Imagine that you're making this measurement for real in the laboratory. Let's start at pH 2 for argument's sake. You've added excess solid. You've measured the solubility. So in this case, pH 2 solubility is quite low, not much above 0 really. And if you were to take the excess material out, you'll see it's free acid. Same thing with making this measurement. Add base, titrate that in, increase the pH. And what you'll find is the solubility isn't really changing very much until we approach pH max. Then there'll be a rapid increase in solubility. And then there'll become a point at which, as you're adding base, the pH does not increase. It does not increase because every molecule of base that you add is converting one molecule of free acid to a salt. Okay, again, same deal as before. Lots of excess solid, lots of base required to complete that conversion. Once the conversion is complete, you carry on adding base, the pH will rise. When you look at the excess solid, it will be a salt. It's kind of difficult in your head to imagine that you've tried to measure the solubility of your salt at low pH. So let's say you made this measurement, you take your salt, you add it to a pH 1 solution. You let it sit, you stir it, and you measure the solubility, it's kind of hard in your head to imagine that that excess solid which is left over is not actually the salt. But it's not the salt because it's actually converted back to the free acid just because of the basic chemistry. No pun intended, because of the basic chemistry which is going on here. Okay. So this concept that what you add into the solution can change is kind of underpinning everything that we're talking about with salts. You've got to recognise that a salt is stable at one pH, but actually it's not stable at another pH because the chemistry involved will convert it back to either the free acid or the free base, depending on what it is. And it's really easy not to notice that. And then you can get all sorts of effects in vivo that you're not understanding because you don't recognise that what you've given the patient is not what's actually in the gastrointestinal tract. Now, as I said already, this is a really difficult concept. And if we were talking about this in class, I would normally stop at this point and say, is everybody okay with this, or do we need to go through it one more time? And I guarantee you a large portion of the class want to go through it again. So if you're sitting there right now thinking, now I've listened to that and I don't quite understand what it is that you're talking about, that's fine. Don't panic. Loads of people are thinking that right now. All you've got to do is pause the video, go back, watch the explanation again, see if it becomes clearer after a couple of viewings. If it doesn't, just drop me an email and I'll do my best to explain it in different words. Okay? But everyone's feeling a bit shaky about it right now, unless you've come across this concept before. So, on the screen are some bullet points to just summarise everything you need to know about pH max right now before we look at what it means for behaviour of salts in vivo. The first point is the pH max is in principle a single point on that curve. It's the point of intersection between two solubility profiles. There is excess solid in these measurements when you make the measurement of solubility, because there has to be, because solubility is a position of equilibrium between dissolved solute and excess solid. If you add acid or base, then what will happen is you're moving up and down that pH curve and you will convert either the free acid or base to the salt or vice versa. When you do that as a titration at the pH max, there will be no increase in pH because there is a conversion from salt to free acid or base or vice versa. For a basic compound, the salt will form if the pH is below the pH max, and for acidic compound, the salt will form if the pH is above pH max. What does this mean for when a salt goes down the GI tract? So I asked you to have a little think about it already. So on the slide in front of you, it just shows you the same graph we looked at earlier for a basic salt. But at the bottom, I've written on there where along the GI tract you might find pHs of certain values. Very clearly, when you swallow a tablet, the first place it's going to end up is the stomach. So the stomach's going to have a pH around about 1.5 to 3. So that's going to be on the left-hand side of our graph. So you can see the word stomach written on the bottom there. If what you swallowed is a basic salt, then what that means is at low pH, any solid which does not dissolve is going to remain as a salt. Okay, so you swallow the salt, it goes into your stomach acid, it remains as the salt. Now think about what happens when the stomach empties into the small intestine. There's going to be a rise in pH, probably to around about 5, maybe 5.5. And as you go down the GI tract, it's going to get higher, probably closer to around 7. So again, I've written that on the lower part of this graph. I hope you can see that as the material empties from the stomach and arrives in the small intestine, if the pH goes to 5, 5 is above the pH max. And that has a consequence in this case, the consequence being any undissolved drug is going to convert to the free base. Another way of thinking about this is to look at the solubility curve, and you can see that the solubility at pH 5 is way lower than the solubility at pH 4 and below. So imagine that you've swallowed this basic salt and it's got into the stomach. It should dissolve quite a lot because it's got a high solubility, and any excess solid left over is going to remain as the salt. When it empties into the small intestine, the pH rises, it goes above pH max, And this has two consequences. One is that the solubility reduces, so that might cause precipitation of the drug out of solution. And two, if it does precipitate out of solution, it's going to precipitate as the free base. Worse, any solid particles that have left the stomach as a salt are also going to convert to the free base. So what you think you've given to the patient as the salt, actually by the time it's in their small intestine, is the free base. You could argue that you might as well have just delivered the free base in the first place, because that's what's actually there. Unless, in the unlikely scenario, you got absorption of the drug from the stomach, but I think that's very unlikely. So what that means is, from a point of view of immediate release tablets at least, if you put a basic salt into an immediate release tablet, it's not such a bad idea. The tablet should instantly disperse when it gets into the stomach. That should have no consequence for the excess solid, and it should allow the material to dissolve to the highest concentration that it can. When it empties into the small intestine, there'll be a rise in pH, and that has the consequence of potentially precipitating the drug back out of solution and converting any excess solid back to the free base. But even though that sounds relatively dramatic from the point of view of solubility, it still isn't that much of a problem because, as I said earlier, your gut wall is lined with cell membranes and ionized species don't cross into cell membranes. So to get good uptake, you actually want the drug to be in its unionized form. And so this is quite good, and it means that basic salts have exactly the right kind of physicochemical properties for oral drug delivery. It's one of the reasons, I think, why so many drugs that are successful are basic salts, because they have the right properties as they go down the GI tract. Think about the case for acidic salts, which is on the screen in front of you. Now the situation is reversed. When we are below the pH max, then the excess solid is the free acid, but when you're above the pH max, the excess solid is the salt. Think about what that means for when you swallow a tablet containing an acidic salt. And imagine it's an immediate release dispersible tablet. That tablet will disperse in the stomach and the salt will be released. The pH of the stomach is 1.5 to 3, so therefore on the left hand side of this graph, and we're below the pH max. What that means is any of the excess drug which hasn't dissolved is going to convert to the free acid, and the solubility is going to be at its lowest. In this case, solubility is almost zero actually. So you give the salt, but almost immediately it has converted back to the free acid. Then you empty into the small intestine. In this instance, the pH max is around about 8.5. At no point along the GI tract are you ever going to go above the pH max. So as you go down the GI tract, you've always got free acid with very poor solubility. If you made the acidic salt purely to increase the solubility, you're not getting any of that effect in vivo. That's point number one. But it may be the case that you get absorption of the drug because you've got the free acid form. Okay, so that's good. Imagine that the pH max was lower. So imagine it was around about 4.55. As that empties into the GI tract, then any excess solid is going to convert back to the salt. So it's gone from salt to free acid in the stomach, and it will go back from free acid back to salt in the GI tract. And that, although it's good for solubility, may not be good for absorption, because then you've got ionized species going around again. So I hope you can see that basic salts, the chemistry is kind of ideally suited to progression of pH down the GI tract, but acidic salts is not ideal for absorption down the GI tract. And if you're absolutely set on needing the salt, you're probably better off putting that into an enterically coated tablet so that you never expose the salt to gastric acid, because the chances are that's going to convert it back to the free acid, and you might as well have just given the free acid in the first place. So, take-home message here is that salt chemistry, it's not complicated, but because it's so dependent on pH, it's really important in the body, because the body is essentially a series of compartments of different pHs. And you've got to kind of get your head around the fact that what you deliver to a patient isn't necessarily what's going to be absorbed. So we saw an example already of a phosphate salt converting to a chloride salt. So again, you might think you're avoiding the common ion effect, but you're not. And then you've got an example where you give a basic salt, but actually it's the free base which is in the gut, which is actually usually a good thing. You give an acidic salt, and actually you've had all sorts of problems. The stomach can convert it back to the free acid, and then it gets into the small intestine and goes back to the salt again. It's a really complicated situation. And so it's about getting your head around what is happening to my solid as it goes through these various pH changes. If you can get that sorted in your head, then you're kind of set for understanding a lot more about how salts are behaving in vivo. So I'm going to leave you with that. I've said many times, if you don't understand, drop me an email and I'll do my best to try and explain everything. Watch the video back a couple of times, see if you can get your head around it. Next week, when we come back, we're going to look at dissolution, we're going to look at pH microenvironment, and then we're going to bring those concepts together, pH max, pH microenvironment, and see what that means for the stability of salts. So with that, I'm going to leave you to think about it, and I'll see you next week.